Welcome to the Deep Sleep Discoveries channel. Tonight, we journey through one of the universe's most fundamental mysteries, a cosmic constant that weaves through every corner of existence. Light travels through the vast emptiness of space, carrying stories from distant stars, connecting moments across time itself. Just before we begin, if these calm, curious explorations help you unwind or give you a quiet way to end your day, please consider liking and subscribing to the channel. It helps others find their way here too. As you settle into comfort, let your mind drift through these gentle revelations about the speed of light. Each fact a soft stepping stone into deeper rest. Each truth a whisper from the cosmos inviting you toward peaceful sleep. The speed of light in a vacuum is exactly 299,792,458 meters per second, a number so precise that it defines the very fabric of our measurements, carved into the universe's architecture like an eternal law written before time began. This velocity represents not merely how fast light moves, but rather the maximum speed at which anything in our universe can travel. The cosmic speed limit beyond which the laws of physics themselves forbid passage. It is a number that appears again and again throughout nature's deepest equations, connecting energy to matter, space to time, in ways that continue to reveal the universe's elegant mathematical beauty. This constant binds our cosmos together. Light travels at approximately 186,282 miles per second, a distance so immense that human minds struggle to grasp its scale, yet this is the pace at which every photon must eternally move. In the time it takes you to draw a single breath, light could travel around our planet multiple times, racing across continents and oceans with effortless grace. This speed connects us to everything we see, for every image entering your eyes arrives riding upon light's swift current, traveling from object to retina in imperceptible fractions of time. The glow of your bedside lamp, the stars beyond your window, all reach you at this same magnificent velocity. Light could circle Earth's equator 7.5 times in 1 second, completing journeys around our entire world faster than a hummingbird's wing can complete a single beat. Imagine a beam of light launched from where you lie, racing eastward across cities and mountains, over vast oceans, returning to find you haven't moved at all, then continuing this circuit 7 more times in that same breathless instant. Our planet, which feels so large beneath our feet, becomes almost small when measured against light's tremendous speed, a marble that light can embrace multiple times between one heartbeat and the next. This perspective shrinks distance itself. The speed of light is denoted by the letter c in physics equations, a simple symbol carrying profound meaning, derived from the Latin word celeritas, meaning swiftness. This single letter appears in humanity's most famous equation, E equals mc squared, connecting mass and energy through light's squared velocity, revealing that matter itself is frozen light, energy bound into physical form. Physicists write this letter countless times, incorporating it into formulas describing everything from black holes to quantum particles, each appearance a reminder of this fundamental constant. The letter C has become physics' shorthand for the universe's ultimate speed, a linguistic anchor for cosmic law. Nothing with mass can travel at the speed of light, a cosmic prohibition woven into the universe's fundamental structure, ensuring that matter and light remain forever separate in their velocities. As any object with mass accelerates closer to light speed, the energy required to push it faster grows without bound, approaching infinity as speed approaches c, making that final increment of velocity eternally unreachable. This isn't merely a technological limitation, but rather a feature of space-time itself, protecting causality and the logical flow of events throughout the cosmos. Even the smallest particle with mass must always travel slower than light's photons, which alone can touch this maximum velocity. Light's speed is the same in all directions and for all observers, regardless of how fast those observers themselves are moving through space, a fact so counterintuitive that it puzzled physicists for generations. Whether you race toward a beam of light or flee from it, you will always measure its approach at exactly the same speed, an invariance that defies everyday experience but forms the bedrock of Einstein's relativity. This constancy means that light doesn't obey the simple addition of velocities that governs our daily world, where thrown balls travel faster from moving cars. Instead, light maintains its pace eternally, indifferent to the motion of its source or observer. The speed of light is considered a universal constant, unchanging throughout all of space and time, a fixed point in an ever-shifting cosmos. Scientists believe this speed has remained identical since moments after the Big Bang, constant through the universe's expansion and evolution across billions of years. This constancy allows physicists to use light speed as a ruler for measuring the cosmos, confident that this standard doesn't warp or shift with location or era. The immutability of c suggests something profound about the universe's structure, a law so fundamental that existence itself might depend upon its unchanging nature. It is the universe's metronome, keeping perfect time forever. Light travels slower when passing through different materials, its photons interacting with atoms in ways that impede their journey, like a traveler winding through a crowded marketplace rather than racing down an empty road. This slowing doesn't mean individual photons reduce their speed, but rather that they're absorbed and re-emitted by atoms along their path, creating delays that make light's overall progress through the material more leisurely. Different substances slow light by different amounts, each material imposing its own characteristic delay based on how strongly its atoms interact with passing electromagnetic waves. This variation in speed through materials creates many of the optical phenomena we observe daily, from bent straws in water to sparkling diamonds. In water, light travels at about 75% of its vacuum speed, slowing to approximately 225,000 kilometers per second as it moves through this liquid medium. Water's molecules interact with photons as they pass, each interaction creating tiny delays that accumulate into measurable slowing across any significant distance. This reduction in speed causes light to bend when entering water at an angle, the phenomenon of refraction that makes swimming pools appear shallower than they truly are, and creates the visual distortion you notice when placing a pencil in a glass of water. The slowing is temporary and reversible. When light exits water back into air, it accelerates again toward its maximum velocity. In glass, light travels at roughly 66% of its vacuum speed, moving at approximately 200,000 kilometers per second through this transparent solid. The silicon and oxygen atoms that form glass create a dense atomic lattice through which light must carefully thread, each photon's journey becoming an intricate dance of absorption and re-emission. This dramatic slowing makes glass invaluable for lenses, which bend light precisely because of this speed difference between air and glass, focusing rays to create images in cameras, telescopes, and your own eyes. The exact speed depends on the type of glass, with different compositions and densities creating different optical properties for different applications. Galileo attempted to measure light's speed in 1638 using lanterns, positioning observers on distant hilltops who would uncover their lamps in sequence, trying to detect any delay between signal and response. His experiment couldn't succeed because light's speed is far too fast for human reaction times to measure across earthly distances, but his effort represented humanity's first systematic attempt to determine whether light traveled instantaneously or required time for its journey. Galileo concluded only that light's speed must be extraordinarily rapid, far exceeding anything he could measure with the tools available in Renaissance Italy. His failure was itself instructive, suggesting light's tremendous velocity through negative result. Ola first demonstrated light has finite speed in 1676, making one of the most important astronomical discoveries in history, revealing that light does not travel instantaneously, but requires measurable time to cross cosmic distances. Working at the Paris Observatory, Römer carefully timed eclipses of Jupiter's moon Io, noticing that these eclipses occurred earlier than predicted when Earth was moving toward Jupiter, and later when Earth was receding from the giant planet. This systematic timing difference could only be explained if light required additional time to travel the extra distance when Earth was farther from Jupiter. His discovery transformed our understanding of the universe, revealing that we see celestial objects not as they are, but as they were. Römer measured light's speed by observing Jupiter's moon Io, whose regular eclipses behind Jupiter provided a cosmic clock against which to measure light's travel time across space. He noticed that eclipses of Io occurred about 22 minutes earlier when Earth was closest to Jupiter compared to when Earth was farthest away, a discrepancy that puzzled astronomers who expected clockwork precision. Römer reasoned that this 22-minute difference represented the time light needed to cross Earth's orbital diameter, the extra distance light must travel when Earth lies on Jupiter's far side. From this observation, he calculated light's speed at about 220,000 kilometers per second, remarkably close to the true value given the limitations of 17th century astronomical measurements. James Bradley refined measurements in 1728 using stellar aberration, a phenomenon where stars appear to shift position slightly due to Earth's motion through space combined with light's finite speed. Bradley noticed that stars traced tiny elliptical paths in the sky over the course of a year, their positions shifting by about 20 arc-seconds, an amount so small it equals the apparent width of a quarter viewed from over 3 kilometers away. This aberration occurs because as Earth orbits the Sun, we're constantly changing our velocity relative to distant starlight, requiring us to tilt our telescopes slightly forward into Earth's orbital motion, just as falling rain appears to come from ahead when you're driving. From this aberration angle and Earth's known orbital velocity, Bradley calculated light's speed with improved precision. Hippolyte Fizeau measured light's speed on Earth in 1849 using a rotating toothed wheel, creating an ingenious mechanical system that could time light's journey across terrestrial distances. Fizeau placed a rapidly spinning wheel with 720 teeth between a light source and a distant mirror 8 kilometers away, arranging the apparatus so light passed through gaps between the teeth, traveled to the mirror, and returned. At certain rotation speeds, the returning light would be blocked by teeth that had rotated into position during light's round-trip journey, allowing Fizeau to calculate light's travel time from the wheel's rotation rate and tooth spacing. This elegant experiment brought light speed measurement down from the cosmic realm into laboratories, making it an earthly phenomenon humans could study directly. Fizeau's measurement was remarkably close to modern values, yielding a result of 313,000 kilometers per second, only about 4% higher than today's accepted value of 299,792 kilometers per second. This accuracy, achieved with 19th century mechanical devices and without electronic timing, demonstrates the cleverness of Fizeau's experimental design and the precision of his execution. His success proved that careful terrestrial experiments could measure light's speed without requiring astronomical observations, opening new avenues for investigating this fundamental constant. The small discrepancy from modern values arose from limitations in measuring the exact distance to his mirror and determining the precise rotation speed of his toothed wheel, both challenging with the technology available in 1849. Léon Foucault improved the measurement in 1862 using rotating mirrors instead of toothed wheels, refining the technique to achieve even greater precision in determining light's velocity. Foucault's method sent a light beam to a rapidly rotating mirror which reflected it to a distant fixed mirror and back. During the light's journey, the rotating mirror turned slightly, causing the returning beam to reflect at a different angle. By measuring this tiny angular deflection and knowing the mirror's rotation speed and the distance traveled, Foucault could calculate light's speed with unprecedented accuracy for his era. His result of 298,000 kilometers per second came remarkably close to modern values, and his rotating mirror technique would inspire precision measurements for decades to come. Albert Michelson won the Nobel Prize for Precision Measurements in 1907, becoming the first American to receive this honor, recognized for developing revolutionary techniques to measure light's properties with extraordinary accuracy. Michelson spent much of his career obsessively refining light speed measurements, using ever more sophisticated rotating mirror systems that could detect angular changes as small as a few millionths of a degree. His final measurement of 299,796 kilometers per second came within 0.002% of modern values, an astounding achievement for the early 20th century. Michelson's meticulous work elevated experimental physics to new heights of precision, demonstrating that careful measurement could reveal nature's constants to remarkable accuracy, and his techniques influenced generations of physicists who followed. The speed of light was officially defined as exact in 1983, when the international scientific community decided to fix light's velocity at precisely 299,792,458 meters per second by definition rather than measurement. This decision reversed the relationship between distance and light speed. Instead of measuring c using the meter, scientists now define the meter using c, making the meter the distance light travels in exactly 1 divided by 299,792,458 of a second. This redefinition became possible because time could be measured far more accurately than length, with atomic clocks achieving precision that made the previous meter standard seem crude in comparison. By fixing light's speed, science created a more stable foundation for measurement, anchoring distance to the most precisely measurable quantity available: time intervals. Modern measurements use lasers and atomic clocks for precision, combining coherent light sources with timekeeping devices accurate to billionths of a second, creating measurement systems that would seem like magic to earlier generations. Atomic clocks measure time by counting oscillations of specific atomic transitions, currently using cesium atoms that vibrate over 9 billion times per second with extraordinary regularity. Lasers provide light with such pure wavelength and phase coherence that their properties can be measured with comparable precision, allowing scientists to verify light's speed or use it as a standard for calibrating instruments. Together, these technologies have confirmed light's constancy to incredible precision, testing Einstein's predictions across countless experiments and finding them correct to more decimal places than most measurements in science. Light from the Sun takes 8 minutes and 20 seconds to reach Earth, traveling 150 million kilometers across the empty space between our star and our world, a journey we call 1 astronomical unit. This delay means we never see the Sun as it is right now, but rather as it was 8 minutes ago. If our star suddenly vanished, Earth would continue orbiting normally and receiving sunlight for 8 more minutes before the sky went dark and gravity released us. Every sunset you've witnessed occurred slightly over 8 minutes before you perceived it, and every sunrise announces an event already past by the time light reaches your eyes. This temporal displacement reminds us that looking outward into space necessarily means looking backward in time, for light's finite speed makes the universe a vast history book. Sunlight takes 5.5 hours to reach Pluto, traveling across nearly 6 billion kilometers to illuminate the distant, frozen world at our solar system's edge, delivering warmth and light so diminished that noon on Pluto resembles deep twilight on Earth. This extended journey means that when scientists sent commands to the New Horizons spacecraft during its Pluto flyby, each instruction required over 4.5 hours to arrive, and confirmation of successful execution took another 4.5 hours to return, creating 9-hour gaps between action and confirmation. The Sun appears no larger than a bright star from Pluto's surface, a mere point of light in a dark sky, yet still bright enough to cast shadows. This distant outpost reminds us of our solar system's true scale, measured in light hours rather than light minutes. Light from the nearest star, Proxima Centauri, takes 4.24 years to reach us, traveling across 40 trillion kilometers of interstellar space, a distance so vast it defies comprehension despite being our closest stellar neighbor beyond the Sun. When you look at this faint red dwarf through a telescope, you see it not as it is today, but as it was when that light began its journey in 2022, carrying information across the years like a message in a bottle drifting across a cosmic ocean. This nearest star remains unreachably distant by current technology. Our fastest spacecraft would require tens of thousands of years to complete the journey that light completes in just over 4 years. The light year itself becomes our measuring stick for the cosmos, more comprehensible than trillions of kilometers. We measure cosmic distances in light years, defining 1 light year as the distance light travels in a full year, approximately 9.46 trillion kilometers or 5.88 trillion miles of space. This unit transforms incomprehensible numbers into meaningful measures, allowing us to say a galaxy lies 30 million light years away, rather than 283 billion kilometers distant, making the cosmos slightly more accessible to human understanding. The light year elegantly combines space and time, acknowledging that in astronomy these two concepts intertwine inseparably. For every distance we observe automatically corresponds to a journey back through history. When we speak in light years, we speak simultaneously of space and of time, of distance and of history, of separation and of connection through light's eternal journey. 1 light year equals about 5.88 trillion miles, a distance so immense that if you could drive it at highway speeds, the journey would require over 10 million years of continuous travel, outlasting the entire span of human civilization many times over. To visualize this scale, If Earth were a grain of sand, a light year would still extend beyond the Moon's orbit around our actual, full-sized planet. This vast measure becomes our cosmic ruler, the standard against which we gauge distances between stars, the spans across galaxies, the separations between galaxy clusters in the largest structures known to exist. Yet, despite its enormity, a light year represents merely a single step in cosmic terms, for the universe stretches across billions of light years in every direction we can observe. The Milky Way galaxy is about 100,000 light years across. A disc-shaped collection of several hundred billion stars spanning a distance light requires 100 millennia to traverse from edge to edge. Our Sun resides about 26,000 light-years from the galactic center, meaning the light we receive from the galaxy's core began its journey during the last ice age on Earth, when mammoths still roamed and our ancestors were just beginning to create cave art. A beam of light starting at one edge of our galaxy and traveling to the opposite side would complete its journey long after all of recorded human history, all of civilization's rise and fall. This immense scale transforms our galaxy from a simple collection of stars into a vast island of light in space. Light from the Andromeda galaxy takes 2.5 million years to reach Earth, traveling across the intergalactic void that separates our galaxy from our nearest large galactic neighbor, carrying photons that began their journey when our human ancestors were just learning to craft stone tools. When you glimpse Andromeda as a faint smudge in autumn skies, you're seeing that galaxy not as it exists today, but as it existed in Earth's distant past, before modern humans evolved, before ice ages came and went. The light entering your eyes tonight left Andromeda when Homo habilis walked African plains, crossing the emptiness between galaxies at light's unchanging pace, indifferent to the eons passing below. This temporal displacement makes astronomy a form of time travel, every observation a window into the past. The observable universe is about 93 billion light-years in diameter, an almost incomprehensible span that represents the maximum distance from which light has had time to reach Earth since the Big Bang 13.8 billion years ago. This observable region represents only a fraction of the universe's true extent, for light from more distant regions simply hasn't had enough time to complete its journey to our location. The observable universe continues expanding not just through space's expansion but also through time's passage, as each moment allows light from slightly more distant regions to finally arrive. We sit within this sphere of observability like inhabitants of a cosmic island, aware that vast territories lie beyond our light horizon, forever hidden from view by the finite age of the universe and light's finite speed. When we look at distant stars, we see them as they were in the past, viewing their ancient light that has traveled across space and time to reach our eyes, transforming every telescope into a time machine that looks backward through history. The farther we look into space, the further we see into the past, observing galaxies as they existed billions of years ago, their light carrying fossilized information about the early universe. This means astronomers studying distant galaxies are viewing the cosmos's childhood, seeing stars and galaxies that might have evolved dramatically or even died long ago, their current state forever unknowable across such vast distances. The universe's history lies spread before us in layers, each distance a different era, each farther view a deeper glimpse into cosmic time. Light from the Moon takes only 1.28 seconds to reach Earth, traveling the relatively short 384,400 kilometers between our world and its natural satellite, a distance that seems almost intimate after considering light's journey across galaxies. This brief delay means we always see the Moon's position slightly behind where it actually is right now, though the difference remains imperceptible to unaided human observation. When astronauts spoke from the lunar surface to mission control on Earth, their words traveled as radio waves at light speed, creating a 2.6-second round-trip delay that gave Apollo conversations their characteristic stilted rhythm. The Moon's closeness in light-time terms makes it humanity's nearest cosmic neighbor, close enough that communication occurs nearly in real time, close enough to feel almost reachable across the void. Einstein's theory of relativity places light speed as the cosmic speed limit, the maximum velocity at which anything, matter, energy, or information can travel through the universe, a boundary woven into spacetime's fundamental structure. This limit isn't arbitrary, but emerges naturally from the mathematical framework describing how space and time relate to each other, how measurements change between observers in relative motion. Einstein realized that the speed of light must remain constant for all observers, and from this single insight, the entirety of special relativity follows, including time dilation, length contraction, and the equivalence of mass and energy. The cosmic speed limit protects causality itself, ensuring that cause always precedes effect, that the universe maintains logical consistency, that the arrow of time points in one direction throughout the cosmos. As objects approach light speed, their momentum and energy increase toward infinity, requiring ever greater amounts of energy to achieve each incremental increase in velocity, like climbing a mountain that grows steeper with every step. This relationship means that accelerating a massive object to light speed would require infinite energy, an impossible requirement that places the speed of light forever out of reach for anything with mass. The energy required doesn't simply add linearly, but grows explosively as speed approaches c, so that the final fraction of a percent toward light speed demands more energy than all the previous acceleration combined. This mathematical barrier protects the cosmic speed limit more effectively than any physical wall, making light speed an asymptote that can be approached ever more closely but never quite reached. Time slows down for objects moving near light speed, a phenomenon called time dilation, where moving clocks tick more slowly relative to stationary ones, though each clock keeps perfect time in its own reference frame. This isn't a mechanical effect or observational illusion, but rather a fundamental property of spacetime itself, confirmed by countless experiments including atomic clocks flown on aircraft that return having measured slightly less elapsed time than identical clocks left on the ground. An astronaut traveling at near light speed would age more slowly than people remaining on Earth, experiencing less subjective time during the journey, returning to find that more time has passed for the rest of humanity. This time dilation becomes more extreme as velocity increases, approaching infinite slowing as speed approaches light speed, warping the traveler's experience of time itself. As speed approaches light speed, time dilation approaches infinity for that object, meaning that a traveler moving at very nearly light speed would experience almost no passage of time during journeys that take years or centuries as measured by stationary observers. This extreme time dilation creates a strange asymmetry. A spacecraft accelerating to 99.9999% of light speed could cross the galaxy in just a few subjective years for its crew, while tens of thousands of years pass for civilizations they left behind. For a photon itself, which travels exactly at light speed, time becomes a meaningless concept, for it exists in no reference frame where it is ever at rest, experiencing no duration between emission and absorption across any distance. This suggests that from light's perspective, if such a perspective could exist, departure and arrival are simultaneous. The entire universe collapsed into a single timeless instant. Light experiences no passage of time from its own reference frame, existing in a timeless state where emission and absorption are simultaneous events, separated by zero subjective duration regardless of the distance traveled. This strange property arises because photons travel at exactly the cosmic speed limit, existing in a condition so extreme that normal concepts of time and duration simply cease to apply. A photon emitted from a distant galaxy 13 billion years ago, from our perspective, experienced no time at all during its cosmic journey, arriving at your eye in the same instant it left its stellar source, the intervening eons compressed into nothingness by light's unique relationship with spacetime. This timelessness of light suggests something profound about the nature of the universe, hinting that time itself might be an emergent property rather than a fundamental feature of reality. Objects contract in length as they approach light speed, a phenomenon called length contraction, where distances shrink along the direction of motion, though this contraction is only observed by external observers and not by travelers themselves. A spacecraft accelerating toward light speed would appear increasingly flattened to stationary observers, its length in the direction of travel compressing towards zero as its velocity approaches c. Remarkably, travelers aboard the spacecraft would notice nothing unusual about their own length. Instead, they would observe the universe outside contracting, distances to their destination shrinking as their speed increases. At extreme velocities approaching light speed, the universe ahead would appear compressed into a thin disk, while time dilation and length contraction conspire to allow travel across vast distances in brief subjective time, making the galaxy itself seem smaller to near-light speed voyagers. The speed of light connects space and time in spacetime, Einstein's unified framework where these previously separate concepts merge into a single four-dimensional continuum, with time serving as a fourth dimension interwoven with space's three dimensions. In spacetime diagrams, light travels at a 45-degree angle, representing 1 light second of distance per second of time, and this angle defines the ultimate limit for possible motion. The speed of light essentially serves as a conversion factor between space and time, allowing us to measure distance in seconds, light seconds, or duration in meters, the distance light travels, revealing their deep equivalence. This unification transformed physics, showing that space and time aren't fixed stages on which events occur, but rather dynamic, interconnected aspects of a single entity that curves, stretches, and interacts with matter and energy. E equals mc squared shows the relationship between energy, mass, and light speed, revealing that mass and energy are equivalent, two manifestations of the same fundamental quantity, interconvertible through the speed of light squared. This elegant equation tells us that mass is simply incredibly concentrated energy, and a small amount of mass corresponds to an enormous amount of energy because c squared is such a colossal number. The equation explains how nuclear reactions release tremendous power by converting tiny fractions of mass into energy, why the sun shines steadily for billions of years, and how particle accelerators can create new particles from pure energy. Einstein's equation unified two concepts previously thought completely separate, showing that the distinction between matter and energy is less fundamental than humanity had believed, with light speed serving as the bridge between these two aspects of existence. Light speed squared, c squared, is an enormous number, approximately 90 quadrillion when expressed in standard units of meters squared per second squared, or about 9 times 10 to the 16th power, a value so large it defies intuitive understanding. This immense number explains why even tiny amounts of mass contain staggering quantities of energy according to E equals mc squared, why nuclear weapons release such devastating power from small amounts of fuel, and why stars can burn steadily for billions of years on limited fuel supplies. Squaring light's already tremendous speed produces a number on a scale rarely encountered in everyday life, bridging the seemingly disparate realms of matter and energy. This mathematical relationship transforms our understanding of existence itself, revealing that the solid matter comprising our bodies, our world, and everything we see represents energy in an incredibly concentrated form. Photons, light particles, are always moving at light speed from the moment they're created until the instant they're absorbed, never accelerating, never slowing in vacuum, existing only in eternal motion at the cosmic maximum velocity. Unlike massive particles that can exist at rest or move at various speeds, photons know only one pace, the speed designated by c, the pace at which electromagnetic waves propagate through empty space. This eternal motion means photons experience no time in their own reference frame, existing in a timeless state between emission and absorption, simultaneously created and destroyed from their own perspective. Photons cannot slow down or stop in vacuum, because doing so would violate the fundamental equations of electromagnetism, would require them to have mass which they don't possess, would break the very laws of physics that allow them to exist. Photons have no mass, allowing them to travel at maximum speed, unencumbered by the inertia that limits particles with mass to speeds below light speed. This masslessness is fundamental to photons' nature as carriers of electromagnetic force, particles that mediate interactions between charged objects across space. Having no rest mass, photons nonetheless carry momentum and energy, can exert pressure on objects they strike, and contribute to gravitational effects through their energy content according to Einstein's mass-energy equivalence. The photon's masslessness and its motion at light speed are inseparably linked. If photons had any mass at all, even infinitesimally small, light speed would be unattainable, and the entire structure of electromagnetism and relativity would collapse into impossibility. Massive particles with infinite energy would approach but never reach light speed, forever asymptotically approaching this cosmic limit without quite attaining it, no matter how much energy propels them forward. As particles accelerate closer to light speed, The energy required for each additional increment of velocity grows without bound, so that adding more and more energy produces smaller and smaller increases in speed. In particle accelerators like the Large Hadron Collider, protons reach 99.9999991% of light speed, yet this final 10 millionth of a percent remains forever beyond reach despite the accelerator's tremendous power. This asymptotic approach to light speed creates a natural boundary in the universe, ensuring that light and only light, along with other massless particles, can travel at the cosmic speed limit, preserving the special status of c in physical law. The speed of light determines causality in the universe, defining what events can influence other events, establishing which parts of spacetime can affect which other parts, creating the fundamental structure of cause and effect. An event can only influence another event if light could travel between them, so the speed of light defines a light cone in spacetime that separates potentially causal relationships from regions where no influence is possible. Events outside each other's light cones are absolutely separated, unable to affect one another, existing in a relationship of pure independence where neither can be said to occur before or after the other in any absolute sense. This light speed limitation on causality prevents paradoxes, ensures that the universe maintains logical consistency, and creates the arrow of time that structures our experience of reality, making the future definitively different from the past. No information can travel faster than light, a principle that protects causality and prevents paradoxes from arising in the universe, ensuring that messages always travel from past to future, never from future to past. This limitation applies not just to visible light but to all information transmission. Radio waves, matter, gravitational influences, quantum correlations, any conceivable signal or message between 2 points in space. Even quantum entanglement, despite its spooky instantaneous correlations, cannot transmit information faster than light, preserving relativity's foundation. This cosmic information speed limit creates a kind of horizon around every event, a boundary beyond which that event cannot yet have any influence, expanding outward at light speed as time passes, gradually extending each occurrence's potential reach through the universe. Light speed keeps cause and effect in proper order throughout the cosmos, preventing the logical contradictions that would arise if effects could precede their causes, maintaining the coherent narrative structure of spacetime. If faster-than-light travel or communication were possible, relativity's equations show that different observers would disagree on the order of events, with some seeing cause before effect while others saw effect before cause, creating impossible scenarios. The cosmic speed limit ensures that all observers agree on causation's direction, even if they disagree on exact timing, preserving the logical consistency that makes physics possible. This protection of causality might be the universe's most fundamental feature, more important than any specific force or particle, for without it, existence itself would descend into incoherent paradox. Light slows to about 200,000 kilometers per second in diamond, reduced to roughly 67% of its vacuum speed by the dense crystalline structure of carbon atoms arranged in diamond's rigid lattice. This dramatic slowing occurs because photons interact strongly with diamond's tightly bound electrons, being absorbed and re-emitted repeatedly as they pass through, each interaction creating a tiny delay that accumulates into measurable reduction. Diamond's high refractive index, which quantifies how much it slows light, explains the gem's extraordinary brilliance, for light entering at one angle exits at a sharply different angle due to refraction, bouncing internally off diamond's faces multiple times before emerging in a display of dispersed colors. This slowing transforms ordinary white light into rainbow fire, making diamond sparkle with the beauty born from light's careful dance through crystalline carbon. The refractive index measures how much light slows in a material, defined as the ratio of light's vacuum speed to its speed in that substance, a number always greater than 1 for transparent materials. Water has a refractive index of about 1.33, meaning light travels at 1 divided by 1.33, or roughly 75% of its vacuum speed through water, while diamond's refractive index of about 2.42 indicates light travels at merely 41% of its maximum speed through this dense crystal. Different materials slow light by different amounts based on how their atomic structure interacts with electromagnetic waves, and this variation creates the optical effects we observe daily. The bending of light at boundaries, the focusing power of lenses, the separation of colors in prisms. The refractive index serves as each material's optical fingerprint, characterizing how it redirects and reshapes light passing through. Light bends when entering different materials due to speed changes, a phenomenon called refraction that occurs whenever light crosses boundaries between substances with different refractive indices, like moving from air into water or glass into diamond. This bending happens because light waves travel at different speeds on either side of the boundary, causing the wavefront to pivot like a car entering sand at an angle, with one wheel slowing before the other. The amount of bending depends on both the speed change and the angle of approach, with light entering perpendicular to a surface passing straight through, while light striking at shallow angles bends more dramatically. This simple physical principle enables lenses to focus light, prisms to disperse white light into rainbows, and optical fibers to trap and guide light around curves through total internal reflection. This bending creates rainbows through water droplets, transforming invisible principles of physics into spectacular arcs of color painted across the sky after rainstorms pass and sunlight illuminates moisture-filled air. Each raindrop acts as a tiny prism and mirror combined. Sunlight enters the drop, slows and bends at the air-water boundary, reflects off the back inner surface, then exits and bends again, emerging at different angles depending on wavelength. Red light, which refracts less than blue, exits at a shallower angle, creating the rainbow's outermost arc, while blue and violet light bend more sharply, forming the inner bands. You see rainbow light from countless droplets simultaneously, each drop contributing only one color to your eye, their collective effect creating the continuous arc that has inspired wonder throughout human history. Light travels fastest in the vacuum of space, achieving its maximum possible speed in the absence of matter, moving at the cosmic speed limit through the nearly empty regions between stars and galaxies. This maximum speed occurs because vacuum offers no atoms or particles for photons to interact with, no delays from absorption and re-emission, nothing to impede their progress as they race across the cosmos. Even the quantum vacuum, which quantum mechanics reveals as seething with virtual particle pairs constantly appearing and vanishing, doesn't meaningfully slow light's propagation compared to the interactions that occur in material substances. The near-perfect vacuum of intergalactic space provides light's ideal medium, allowing photons to maintain their maximum velocity across billions of light-years, carrying information about distant galaxies without interference or degradation from their journey through emptiness. Air slows light by only about 0.03% compared to vacuum, a nearly imperceptible reduction that makes Earth's atmosphere essentially transparent to electromagnetic radiation, allowing us to see stars almost as clearly as if we were in space. Air's low density means photons encounter relatively few molecules during their passage, experiencing occasional interactions but mostly traveling through empty space between widely separated nitrogen and oxygen molecules. This minimal slowing explains why we rarely notice refraction effects when looking through horizontal air, though you can observe atmospheric refraction by watching stars twinkle, their light bent chaotically by turbulent air currents. The atmosphere's refractive index of about 1.0003 makes it nearly optically equivalent to vacuum, permitting astronomy from Earth's surface and allowing sunlight to reach the ground at essentially full light speed. Scientists have slowed light to about 17 meters per second in ultra-cold sodium in 1999, reducing light speed to less than 1/10,000,000th of its vacuum velocity, slowing it to bicycle speeds through quantum manipulation of matter's interaction with electromagnetic waves. Physicist Lena Howe and her team at Harvard cooled sodium atoms to within a few billionths of a degree above absolute zero, creating a Bose-Einstein condensate where atoms lose their individual identities and behave as a single quantum entity. By carefully tuning this condensate with laser light, they created conditions where incoming light pulses coupled to the atom's quantum states, transferring their energy into collective excitations that propagated at bicycle speeds through the atomic cloud. This dramatic slowing isn't just a curiosity but demonstrates exquisite quantum control, opening possibilities for storing light's quantum information in matter, potentially useful for future quantum computers and communication systems. In 2001, light was brought to a complete stop and then released in laboratory experiments, achieving what seems impossible: temporarily capturing light in matter, holding it motionless, then releasing it to continue its journey, like pressing pause on a cosmic speed demon. Researchers accomplished this by sending light into a specially prepared Bose-Einstein condensate, then turning off the coupling laser that allowed light to propagate through the ultra-cold atoms, effectively freezing the light pulse's quantum information into the atom's collective quantum state. The light didn't exist as photons during storage, but rather as patterns of atomic excitation, its information preserved in quantum form until researchers reactivated the coupling laser, releasing the stored information as new photons that continued propagating with their original properties intact. This stopped light research explores the boundary between light and matter, quantum and classical, motion and stillness. When light stops, its information is stored in atomic quantum states and then regenerated, transforming photons into matter waves and back again through quantum processes that preserve the light's original properties across the transition. This isn't truly stopping light in the sense of freezing individual photons in place, for photons by nature cannot stop or slow. Rather, it's converting light into a different form, much as water converts to ice and back. The atom's quantum states encode everything about the original light pulse, its frequency, phase, even quantum entanglement, holding this information stationary until conditions change to release it. This quantum storage could enable future quantum computers to interface light-based communication with matter-based processing, or create quantum memories that preserve fragile quantum information against decoherence, building blocks for quantum internet spanning continents through fiber optic cables. Light travels at about 200,000 kilometers per second in optical fibers, carrying internet traffic, phone calls, and streaming videos through glass cables thinner than human hairs at 2/3 of vacuum light speed. These fiber optic cables guide light through total internal reflection, a phenomenon where light striking the glass cladding boundary at shallow angles reflects completely back into the fiber core, bouncing along the cable's length without escaping. The reduced speed in glass fiber still allows information to cross oceans in fractions of a second, making real-time global communication possible, though the speed reduction compared to vacuum creates measurable delays in high-frequency trading where milliseconds matter. Modern internet infrastructure depends on this slowed light in glass, with millions of kilometers of fiber optic cable spanning continents and crossing ocean floors, each strand carrying countless conversations and data streams at a significant fraction of the cosmic speed limit. GPS satellites must account for light speed to provide accurate positioning, because radio signals from satellites to receivers take measurable time to propagate, and even nanosecond errors in timing would translate to meters of position error. GPS works by measuring precisely when signals from multiple satellites arrive at your device. By comparing these arrival times and knowing the satellite's positions, your receiver calculates its location through trilateration. Light speed means signals from satellites 20,000 kilometers overhead take about 67 milliseconds to arrive, and this delay must be precisely accounted for in timing calculations. Without correcting for light travel time and also relativistic effects that make satellite clocks run slightly faster than ground clocks, GPS would accumulate position errors of kilometers per day, rendering the system useless for navigation. Fiber optic internet relies on light traveling through glass cables, encoding information in pulses of laser light that race through strands of ultra-pure glass at about 2/3 of light's maximum speed, carrying the entirety of global internet traffic. These optical fibers transmit data as rapid on-off patterns of light, with billions of pulses per second streaming through each strand, each pulse representing a digital bit in the endless flow of emails, videos, web pages, and video calls circling the planet. The glass used must be extraordinarily transparent, purer than window glass by many orders of magnitude, allowing light to travel dozens or hundreds of kilometers before needing amplification. This infrastructure makes modern life possible, connecting continents within milliseconds, making distance nearly irrelevant for information exchange, though light's finite speed still creates noticeable delays in intercontinental video calls. Light speed limits how fast computers can process information, because signals between components must propagate at light speed or slower, and even at this maximum velocity, light travels only about 30 centimeters per nanosecond in air. Modern processors run at gigahertz speeds, executing billions of operations per second, meaning each computational step occurs in nanoseconds or less, during which light travels distances measured in centimeters. This fundamental limitation explains why computer components must be packed tightly together, why the distance between processor and memory matters for performance, and why future speed improvements face a wall imposed by light's finite velocity. Even if we could somehow make infinitely fast electronic switches, they could only communicate at light speed with nearby components, creating an ultimate limit on how fast computers can compute regardless of technological advances in component miniaturization. The distance between computer components affects processing speed because signals take time to propagate even at light speed, making physical layout crucial for high-performance computing where nanoseconds matter. Engineers designing supercomputers carefully minimize wire lengths between processors and memory, between different processor cores, between any components that must communicate frequently and rapidly. In modern processors, some operations are slowed not by the computational elements themselves, but by the time required for signals to propagate across the chip, with light's finite speed becoming the bottleneck. This geographical limitation on computation explains why quantum computers exploring non-local correlations might offer advantages and why future computing architectures must increasingly consider physical topology, not just logical connections, with component spacing becoming as important as component speed in the eternal race for faster computation. Laser measurements use light speed to calculate distances precisely, sending laser pulses to targets and measuring the round-trip time with exquisite accuracy, determining distance by multiplying half the round-trip time by light's speed. Surveyors use these laser rangefinders to measure building dimensions. Scientists use laser altimetry to map terrain from aircraft. And engineers use laser scanners to create three-dimensional models of complex structures. The precision achievable depends on how accurately time can be measured. Modern systems with atomic clock-based timing can measure distances to millimeter accuracy across kilometers. This technique even extends to space. Scientists bounce laser beams off retroreflectors placed on the Moon by Apollo astronauts, measuring Earth-Moon distance to millimeter precision by timing the 2.6-second round-trip journey, detecting the Moon's gradual recession from Earth at about 3.8 centimeters per year. Radar uses reflected light waves to determine object distances, though typically employing radio waves rather than visible light, both traveling at the same fundamental speed determined by c, both following identical principles of reflection and propagation. Radar systems emit radio pulses and listen for echoes, measuring the time delay between transmission and reception, calculating target distance from round-trip time divided by 2 and multiplied by light speed. This technology enables air traffic control to track aircraft, allows ships to navigate safely in fog, helps meteorologists detect and track storms, and enabled the first maps of Venus's surface beneath its impenetrable cloud layers. The same principle extends to light-based LiDAR, microwave-based radar, and radio wave-based deep space tracking, all variations on the theme of timing electromagnetic wave reflection to measure distance across the cosmic speed limit. Light speed enables LiDAR technology for mapping and autonomous vehicles, sending millions of laser pulses per second in all directions and measuring each return time to create detailed three-dimensional maps of surroundings. Autonomous vehicles use LiDAR to see their environment, detecting pedestrians, other vehicles, road boundaries, and obstacles by analyzing the distance to every point surrounding the vehicle, updated continuously as the car moves. Each laser pulse's round-trip time reveals the distance to whatever surface reflected it, and by scanning systematically in all directions, LiDAR builds a point cloud representation of three-dimensional space. This technology relies entirely on light speed's constancy. If light speed varied unpredictably, LiDAR distance measurements would be unreliable, and the precise environmental mapping required for safe autonomous navigation would become impossible, grounding self-driving cars and robotic systems that depend on understanding their spatial relationships with surrounding objects. Astronomers use light speed to calculate distances to celestial objects, combining measured light travel times with known velocities to determine cosmic separations, or using the relationship between apparent and intrinsic brightness of distant objects whose light has traveled known durations. For relatively nearby objects, measuring parallax as Earth orbits the Sun reveals distances through geometry, but this method fails for distant objects, requiring astronomers to use standard candles, objects of known intrinsic brightness, whose apparent dimness indicates their distance through light's inverse square law. Distant supernovae serve as standard candles for measuring cosmic expansion, their known brightness and observed dimness revealing distances light traveled over billions of years. These measurements revealed the universe's accelerating expansion, unexpected evidence for dark energy discovered by carefully measuring the relationship between distance and redshift, between light travel time and wavelength stretching, all depending fundamentally on light speed's constancy across cosmic expanses. Synchronizing clocks across long distances requires accounting for light speed because any signal used to coordinate clocks travels at finite velocity, arriving with a delay that must be corrected to achieve accurate synchronization. GPS satellites maintain precise synchronized time by constantly exchanging signals and accounting for propagation delays, implementing sophisticated algorithms that factor in relativity's effects on time as well as light's finite speed. International time standards depend on coordinating atomic clocks worldwide, but light speed means signals comparing one clock to another take measurable time to propagate, with clocks in Australia and Europe separated by dozens of milliseconds in light travel time. Scientists solved this by defining simultaneity relative to light speed itself, using Einstein's synchronization convention that accounts for finite signal propagation, making distant clock coordination possible despite the fundamental limitation that no information travels instantaneously across space. Particle accelerators push particles to 99.9999% of light speed, accelerating protons or electrons through powerful electromagnetic fields until they race around circular tracks at velocities where relativistic effects become pronounced and impossible to ignore. The Large Hadron Collider accelerates protons to 99.9999991% of light speed, so close to C that these particles complete the LHC's 27-kilometer circumference 11,245 times per second, experiencing extreme time dilation where their internal clocks run thousands of times slower than stationary clocks. At these extreme velocities, the energy required for additional acceleration grows enormously, with most energy going not into speed increase but into relativistic mass increase, demonstrating light speed as an asymptotic limit. These particle collisions at near light speeds recreate conditions from the universe's first moments after the Big Bang, probing physics at energy scales unavailable elsewhere, revealing fundamental particles and forces through energies achievable only by approaching light's cosmic speed limit. The speed of light limits how quickly we can communicate with space probes, creating unavoidable delays in commanding distant spacecraft and receiving their data, making space exploration an exercise in patience and careful planning. Commands sent to spacecraft must account for light travel time. Engineers cannot control rovers or probes in real time, but must send instructions that account for where the spacecraft will be when commands arrive. These delays necessitate autonomous systems on distant probes, computers capable of making decisions without waiting for instructions from Earth, responding to unexpected situations faster than light-speed communication allows. For distant missions like New Horizons at Pluto or Voyager in interstellar space, the communication delay transforms mission operations from interactive control to scheduled programming, with spacecraft executing pre-planned sequences because real-time guidance is impossible across light hours of distance separating humanity from its mechanical explorers. Messages to Mars rovers take between 3 and 22 minutes one way, depending on where Earth and Mars lie in their respective orbits, creating communication delays that range from short pauses to lengthy gaps when the planets occupy opposite sides of the Sun. During close approach, when Mars and Earth are on the same side of the Sun, signals cross about 55 million kilometers in roughly 3 minutes, allowing relatively responsive communication, though still too slow for real-time control. During opposition, when planets lie on opposite sides of their orbits, signals must travel 400 million kilometers, requiring over 22 minutes one way, making round-trip communication take nearly an hour. These light-speed delays fundamentally change how rovers are operated. Drivers on Earth cannot steer in real time, but must plan routes carefully, analyzing images and terrain data to chart safe paths that rovers then execute autonomously, while new commands slowly crawl across interplanetary space. Voyager 1's signals take over 22 hours to reach Earth, crossing more than 24 billion kilometers of space at light speed, carrying data from humanity's most distant ambassador as it explores the region beyond our Sun's influence. Launched in 1977, Voyager 1 continues transmitting despite its immense distance, though its signals arrive at Earth unimaginably weak, requiring the most sensitive receivers ever built to detect whispers of data crossing light hours of space. Commands sent to Voyager take equal time to arrive, meaning any instruction sent today won't reach the spacecraft until tomorrow, and confirmation of successful execution won't return until the day after, creating a communication delay longer than human attention spans comfortably encompass. This light-hour separation reminds us that Voyager truly explores alien territory, so distant that light's tremendous speed seems inadequate to bridge the gulf between humanity's home and its most distant creation. Light-based distance measurements helped detect gravitational waves, the LIGO observatory using laser interferometry to measure changes in distance smaller than an atomic nucleus, detecting the space-stretching effects of gravitational waves from merging black holes billions of light-years away. LIGO splits laser light between two perpendicular arms several kilometers long, comparing how long light takes to travel down each arm and return. When a gravitational wave passes, it stretches space along one direction while compressing it in the perpendicular direction, causing light in one arm to take slightly longer to complete its journey than light in the other arm. This time difference, though incredibly tiny, changes lasting only thousandths of a second in paths differing by fractions of a proton width, becomes detectable through laser interferometry, comparing light travel times with extraordinary precision. These detections opened gravitational wave astronomy, a new way of observing the cosmos that complements light-based astronomy, both depending fundamentally on electromagnetic wave propagation at the cosmic speed limit. The speed of light determines the resolution limits of microscopes because light's wavelength sets a fundamental boundary on the smallest details that can be resolved, with objects smaller than half the wavelength becoming impossible to distinguish individually. Visible light with wavelengths between 400 and 700 nanometers cannot resolve details smaller than about 200 nanometers, roughly 1/5000th of a millimeter, a fundamental limit that no amount of magnification can overcome. This resolution limit arises from light's wave nature. Waves diffract around small objects, and when objects are closer together than half a wavelength, their diffraction patterns overlap inseparably, preventing individual resolution. Electron microscopes overcome this limit by using electrons with much shorter wavelengths than light, while super-resolution optical microscopy cleverly circumvents the diffraction limit through fluorescence techniques. But the fundamental relationship between wavelength and resolution stems from light speed determining the relationship between frequency and wavelength in electromagnetic waves. Virtual particles can briefly exceed light speed without violating relativity, existing for such short durations that they remain consistent with quantum uncertainty, borrowing energy from vacuum for time intervals too brief to precisely measure, these temporary fluctuations causing no contradictions with causality. In quantum field theory, virtual particles constantly appear and vanish throughout space, mediating forces between real particles, creating the quantum foam underlying reality at the smallest scales. These virtual particles differ fundamentally from real particles. They need not satisfy the normal relationship between energy and momentum that limits real particles to speeds below c, existing only as mathematical terms in quantum calculations rather than as truly observable entities. Their apparent speed violations pose no problems because they cannot transmit information, cannot create causal paradoxes, and exist for durations so brief that Heisenberg's uncertainty principle prevents precise, simultaneous measurement of their position and momentum anyway. Quantum entanglement appears instantaneous but transmits no information faster than light, preserving relativity despite the spooky correlations that puzzled Einstein and continue challenging our intuitions about reality. When particles become entangled, measuring one instantly determines the other's state regardless of separation, as if information traveled faster than light between them. Yet careful analysis reveals no usable information transmission occurs. The correlations exist but cannot be controlled. You cannot force your measurement to produce a particular result and thereby signal a distant partner, because quantum measurements yield fundamentally random outcomes. Only by later comparing measurement results through conventional light-speed limited communication do observers discover the correlations existed, realizing their measurements were mysteriously linked despite their separation. This subtle distinction preserves causality while allowing quantum mechanics' strangest predictions, demonstrating how the universe can be simultaneously deeply interconnected yet locally causal, mysterious yet consistent. Cherenkov radiation occurs when particles travel faster than light in a medium, creating an electromagnetic shockwave analogous to sonic booms when aircraft exceed sound speed in air, though no violation of light speed in vacuum occurs. This phenomenon arises because light travels slower in materials than in vacuum, so particles accelerated to high velocities can exceed light's reduced speed in that medium even while remaining below the ultimate vacuum light speed. When a charged particle moves faster than light's phase velocity in a medium, it creates a cone of blue light, the electromagnetic equivalent of a sonic boom, as the particle essentially outruns the electromagnetic disturbances it creates in the medium. This blue glow serves as a beautiful signature of high-energy particles exceeding local light speed without violating cosmic law, possible only because the speed limit applies to vacuum light speed, not to light's reduced velocity in materials. Cherenkov radiation creates a blue glow in nuclear reactors, the eerie azure light visible in cooling pools surrounding nuclear fuel rods, where high-energy electrons ejected from radioactive decay travel faster than light speed in water. These electrons accelerated to velocities exceeding water's light speed of about 225,000 kilometers per second, while remaining well below vacuum light speed of 300,000 kilometers per second, emit the characteristic blue Cherenkov radiation as they race through the cooling pool. The glow provides a visible indicator of radioactivity, a beauty born from nuclear decay, and scientists use specialized Cherenkov detectors to identify high-energy particles in experiments, the radiation serving as a telltale signature of particles exceeding local light speed. This phenomenon demonstrates relativity's subtlety. Light speed as a limit applies specifically to vacuum, and particles can exceed light's reduced speed in materials without violating fundamental law, creating luminous evidence of their superluminal journey through media. Neutrinos travel extremely close to light speed, these nearly massless particles racing across the universe at velocities differing from c by tiny fractions, passing through matter almost unimpeded, ghost-like messengers from stellar cores and cosmic catastrophes. For decades, scientists believed neutrinos might travel exactly at light speed, possessing zero mass like photons. But experiments eventually revealed neutrinos have tiny masses, meaning they must travel slightly slower than light despite their nearly massless nature. Neutrinos from the Sun arrive on Earth only nanoseconds later than they would if traveling at exactly light speed, a delay so small it's difficult to measure across 150 million kilometers. These particles' extreme speed and minimal interaction with matter allow them to escape from stellar cores where photons remain trapped for hundreds of thousands of years, making neutrinos messengers bringing real-time news from the Sun's center. Early experiments mistakenly suggested neutrinos exceeded light speed in 2011, when researchers at CERN reported neutrinos arriving at a detector in Italy 60 nanoseconds faster than expected, seemingly completing their journey faster than light could travel the same distance. This result shocked the physics community, for if true, it would overturn a century of relativity, requiring fundamental revision of our understanding of space, time, and causality. The measurement seemed careful and systematic, leading to months of scrutiny as physicists worldwide examined the data, proposed explanations, and debated implications. Yet something so fundamentally revolutionary demanded extraordinary evidence, and physicists remained appropriately skeptical, knowing that extraordinary claims require extraordinary proof, suspecting experimental error despite being unable to immediately identify the problem in the complex measurement system. The error was traced to a faulty cable connection, a loose fiber optic cable that introduced timing errors in the GPS system used to synchronize clocks between the neutrino source and detector, demonstrating how even careful experiments can contain subtle systematic errors. This mundane explanation, a loose cable, resolved the mystery after months of investigation, confirming that relativity remained intact, that light speed retained its status as cosmic limit, that no revision of fundamental physics was required. The episode demonstrated science's self-correcting nature. Extraordinary claims underwent extraordinary scrutiny, and the error was eventually found and acknowledged. It also reminded researchers that even sophisticated modern experiments involve mundane physical components, cables, connectors, electronic systems, any of which can introduce subtle errors into precise measurements, and that healthy skepticism toward revolutionary claims remains appropriate until multiple independent confirmations eliminate reasonable doubt. Tachyons are hypothetical particles that would travel faster than light, existing perpetually above the cosmic speed limit, just as ordinary particles exist perpetually below it, occupying a strange theoretical realm where cause and effect become ambiguous. If tachyons existed, they would possess imaginary mass, lose energy as they accelerate, and create numerous causality paradoxes. Observers in different reference frames would disagree on whether a tachyon traveled forward or backward in time, introducing logical contradictions into physics. These particles appear in some theoretical models but have never been observed, and most physicists suspect they don't exist in reality, serving instead as mathematical curiosities demonstrating what relativity forbids. The absence of tachyons appears to be a feature of our universe, not a limitation, for their existence would undermine causality itself, allowing effects to precede causes and creating the possibility of time travel paradoxes that would render the universe logically incoherent. No evidence for tachyons has ever been found, despite decades of searching. No experiments have detected faster-than-light particles. No astronomical observations have revealed superluminal signals, reinforcing the conclusion that light speed represents a true cosmic boundary. Physicists have looked for tachyons in cosmic rays, in particle accelerators, in the products of nuclear reactions, in signals from distant astronomical events, consistently finding nothing exceeding light speed within experimental precision. This negative evidence, accumulated across countless experiments and observations, suggests tachyons remain confined to theoretical speculation rather than physical reality. The universe appears to respect its own speed limit universally, with all particles and forces consistently obeying the constraint that nothing with real mass reaches or exceeds c. A consistency that strengthens confidence in relativity's framework and in the fundamental role of light speed in cosmic structure. The speed of light in quantum field theory defines fundamental interactions, appearing in formulas describing how particles interact through electromagnetic, weak and strong nuclear forces, connecting these forces through relationships that depend on c. In quantum electrodynamics, light speed relates the strength of electromagnetic interactions to fundamental constants, appearing in the fine structure constant that governs how strongly electrons and photons interact. The standard model of particle physics incorporates light speed throughout its mathematical structure, using it to connect space and time derivatives in field equations, to normalize quantum fields, to define the relationship between energy and momentum for both massive and massless particles. This pervasive appearance of c throughout particle physics suggests light speed represents something more fundamental than merely the velocity of electromagnetic waves, perhaps revealing a basic feature of spacetime itself, or indicating that all forces ultimately share a common origin in geometric properties of the universe's fabric. The universe's expansion can make distant galaxies recede faster than light, their distance growing more rapidly than light could travel across the space separating us from them. Yet this violates no physical law because space itself expands rather than galaxies moving through space. This distinction matters crucially. Relativity limits how fast objects can move through space but places no restriction on how fast space itself can expand, creating or destroying distance without anything actually traveling. Galaxies participating in cosmic expansion remain essentially stationary within their local space, carried along by space's expansion like raisins in rising bread dough, their recession arising from the creation of new space between galaxies rather than from motion through existing space. This expansion-driven recession can exceed light speed for sufficiently distant galaxies, meaning their light will never reach us despite having been emitted in our direction, forever separated by space expanding faster than light can traverse it. This doesn't violate relativity because space itself is expanding, creating new distance between objects without those objects actually moving through space, a subtle but crucial distinction that reconciles cosmic expansion with light speed limits. Einstein's equations of general relativity describe not just how matter moves through spacetime but also how spacetime itself can curve, expand and evolve, including solutions where space grows uniformly larger over time. In expanding space, light travels at its usual speed locally, yet the expansion of space through which light moves can cause the total distance between source and destination to grow faster than light can traverse it, like running on a treadmill whose belt accelerates faster than you can run. No information or object exceeds light speed locally, preserving causality. Yet cosmic expansion creates effective recession velocities that can exceed c when calculated across cosmological distances, demonstrating that local and global behavior can differ dramatically in curved, expanding spacetime. Light from the early universe has been redshifted by cosmic expansion, stretched to longer wavelengths as space expanded during its journey across billions of years, transforming ultraviolet light emitted by young stars into infrared radiation by the time it finally reaches our telescopes. This cosmological redshift differs from Doppler shift. It arises not from galaxies moving through space, but from space itself expanding during light's journey, stretching the light waves as the space containing them grows larger. The amount of redshift indicates how much the universe has expanded since the light was emitted, providing a direct measure of cosmic history, with greater redshift corresponding to earlier times when the universe was smaller, younger, hotter, and denser. Astronomers use redshift as a cosmic clock, reading the universe's expansion history encoded in light's stretched wavelengths, tracing cosmic evolution from the earliest observable epochs to the present day through this gradual reddening of ancient light. The cosmic microwave background traveled 13.8 billion years to reach us, though the distance to its source is now about 46 billion light-years due to space's expansion during its journey, a mind-bending consequence of cosmic evolution. This radiation was emitted when the universe was only 380,000 years old, released when electrons and protons first combined into neutral hydrogen, allowing light to travel freely through space for the first time. That primordial light has been traveling toward us ever since, gradually redshifted from visible light to microwaves by the universe's expansion, cooled from thousands of degrees to just 2.7 degrees above absolute zero by space's relentless stretching. We observe this ancient light from all directions, seeing the universe's baby picture projected across the entire sky, the oldest light accessible to observation, carrying information about cosmic conditions from an era when the universe was hot, dense, and remarkably uniform. We can never see beyond our cosmic light horizon, a fundamental boundary beyond which light hasn't had enough time to reach Earth since the Big Bang, creating an observational limit that even perfect telescopes cannot overcome. This horizon exists not because space ends there, but because the universe has finite age. Regions more distant than light could travel in 13.8 billion years remain forever beyond observation, their light still en route and won't arrive for billions or trillions of years. The observable universe forms a sphere around Earth, not because we occupy a special position, but because every observer exists at the center of their own observable sphere, beyond which light hasn't yet had time to arrive. This horizon grows gradually as time passes and light from increasingly distant regions finally completes its cosmic journey, but will always exist as long as the universe has finite age, forever hiding portions of the cosmos from view beyond this light-speed-defined boundary. The light horizon defines the observable universe, marking the maximum distance from which light could have reached us given the universe's finite age and light's finite speed, creating a sphere roughly 93 billion light-years in diameter centered on Earth. This observable region represents only a fraction of the universe's true extent, with current theories suggesting the full universe could be vastly larger, potentially infinite, extending far beyond what we can observe. We see galaxies scattered throughout the observable universe but can never know what lies beyond the light horizon, whether the universe continues uniformly or changes character beyond our observational reach. This horizon reminds us that our knowledge of the cosmos remains fundamentally limited, that vast regions of reality may exist forever beyond human observation, hidden not by cosmic censorship but simply by the combination of the universe's finite age and light's finite speed, creating an inevitable boundary on observation. Dark energy accelerates the universe's expansion faster over time, causing space to expand at an increasing rate, making distant galaxies recede ever more rapidly in a cosmic acceleration that dominates the universe's current evolution. Discovered in 1998 through observations of distant supernovae, dark energy represents an unknown component of the universe that exerts a kind of anti-gravitational effect, pushing space apart rather than pulling it together as ordinary gravity does. This acceleration means that galaxies already receding near light speed will recede even faster in future, eventually exceeding light speed for all but our nearest galactic neighbors, carrying away most of the observable universe beyond our light horizon. The physical nature of dark energy remains mysterious despite its dramatic effects. One of cosmology's deepest puzzles, comprising about 68% of the universe's total energy, yet remaining fundamentally unexplained by current theory. Its presence inferred from cosmic acceleration measured through light-speed limited observations across cosmic distances. Some galaxies will eventually move beyond our light horizon forever, carried away by accelerating cosmic expansion until their light can no longer reach us despite traveling at maximum speed, lost to observation though they continue existing beyond our observable sphere. As dark energy drives faster expansion, the observable universe will eventually stop growing and then shrink, as light from increasingly distant regions fails to overcome space's accelerating expansion, like a swimmer fighting a current that grows ever stronger. In the far future, distant galaxy clusters will fade from view one by one, their light unable to cross the expanding space separating us, eventually leaving only our local galactic group visible while the rest of the universe recedes beyond observation. This cosmic isolation isn't a physical destruction but an observational loss, galaxies continuing their existence while light speed limitations combined with accelerating expansion place them forever beyond human view, demonstrating how light speed defines not just what we can see now but also what we might see in the future. Light speed determines the maximum rate of cosmic information exchange, limiting how quickly information can propagate between distant regions of space, creating a cosmic communication constraint that affects the universe's large-scale structure and evolution. In the early universe, this limitation meant that widely separated regions couldn't exchange information or coordinate their properties before inflation expanded them beyond each other's light horizons. Yet measurements show these now disconnected regions share remarkably similar properties. This similarity, despite causal disconnection, motivates cosmic inflation theory, which proposes a brief period of faster-than-light expansion in the universe's first moments, allowing currently disconnected regions to have been in causal contact before inflation expanded them beyond each other's light horizons. The finite speed of light and information also means that the universe has a kind of memory horizon. Information about events more than 13.8 billion light-years away simply hasn't arrived yet, making the past effectively unknowable beyond certain distances regardless of our technological capability. The finite speed of light means we see the universe's history when we look outward, transforming telescopes into time machines that peer into the past, observing progressively earlier epochs of cosmic history as we examine increasingly distant objects. Looking at a galaxy 1 billion light-years away shows that galaxy as it existed 1 billion years ago, revealing the universe at an earlier stage of evolution when it was younger, smaller, and different from today. The most distant observable objects show the universe in its infancy, revealing conditions and structures from cosmic dawn, the era when first stars and galaxies formed from primordial gas. Astronomy uniquely allows studying history directly through observation rather than through fossilized remains or indirect evidence, for the finite speed of light preserves information about past conditions in the light currently arriving from distant sources, making cosmology simultaneously the study of vast space and deep time, distance and duration merged through light's constant velocity. The meter is now defined based on the speed of light, reversing the historical relationship where light speed was measured using the meter, now fixing c by definition and defining length in terms of this fundamental constant. This redefinition occurred in 1983 when the international scientific community recognized that time could be measured far more precisely than length using atomic clocks, making it more practical to define distance through light speed than to maintain a physical meter standard. The previous meter definition, based on a specific wavelength of krypton 86 light, gave way to the current definition that fixes light speed exactly and defines the meter as the distance light travels in a specific fraction of a second. This change reflects how scientific standards evolve as measurement capability improves, gradually anchoring definitions to ever more fundamental and precisely measurable quantities, ultimately tying many units to fundamental constants like light speed, whose values represent features of nature itself rather than arbitrary human choices. 1 meter is the distance light travels in 1 divided by 299,792,458 of a second, a definition that simultaneously fixes light's speed exactly and defines length in terms of duration, making the meter dependent on time measurement and light's constant velocity. This definition means that as atomic clocks improve and we can measure time with greater precision, our ability to measure length improves automatically, maintaining length standards precision without requiring new physical artifacts. The specific number 299,792,458 was chosen to make the new definition match the previous meter standard as closely as possible, ensuring continuity while improving precision and stability. This definition also means that light speed in meters per second equals exactly 299,792,458 by definition, not by measurement, transforming what was once an experimentally determined quantity into a defined constant that anchors our system of units, elevating light speed from measured property to fundamental definition. The speed of light is exactly 299,792,458 meters per second by definition, fixed precisely rather than measured approximately, making this value absolutely exact with zero uncertainty, unlike almost every other physical quantity. This exactness arises from the 1983 decision to define the meter through light speed, essentially declaring light speed shall be exactly this value and distances shall be whatever makes this statement true. The definition's precision exceeds any measurement's precision. We can never measure light speed more accurately because improving measurement accuracy would simply improve our realization of the meter rather than changing the defined value of c. This exactness reflects a subtle shift in scientific philosophy. Fundamental constants like light speed are now recognized as features of nature so basic that they're better used to define human units than to be measured within those units, transforming certain quantities from experimental results into definitional anchors for measurement systems. This makes the meter dependent on time, not the other way around, reversing the intuitive relationship where distance seems primary and time secondary, instead treating time as the more fundamental quantity from which distance derives. We can now measure time intervals to extraordinary precision using atomic clocks that count quantum oscillations, achieving accuracy to parts in 10 to the 18th, meaning atomic clocks won't gain or lose a second in hundreds of millions of years. Length measurements depend on these precise time measurements combined with light's fixed speed. The better we measure time, the better we measure distance, making temporal measurement the foundation of spatial measurement. This hierarchy reflects physical reality, where time intervals can be measured by simply waiting and counting periodic events, while distances require propagation of signals at finite speed, making time measurement conceptually simpler and practically more precise, justifying its foundational role in defining other quantities including length through light speed's constant velocity. Atomic clocks can measure time intervals with precision beyond a billionth of a second, achieving accuracy that staggers imagination, losing or gaining less than a second over billions of years of continuous operation. Modern atomic clocks use the precise quantum transitions of atoms like cesium or strontium, counting billions of oscillations per second with such regularity that they outperform any mechanical or electronic timekeeping device by factors of billions. These clocks are so sensitive they detect time dilation from height differences of centimeters, measuring gravity's effect on time as predicted by general relativity, confirming Einstein's century-old predictions in laboratory settings. This extraordinary precision enables GPS navigation, tests of fundamental physics, precise synchronization of complex systems, and defines the second as 9,192,631,770 periods of cesium-133's microwave transition, a definition based on counting quantum oscillations rather than astronomical observations, anchoring time measurement to atomic physics rather than Earth's rotation or orbit around the Sun. Modern measurements confirm light speed is constant to incredible precision, testing Einstein's prediction across countless scenarios with ever-improving accuracy, never finding variation in c, despite searching in environments from Earth's surface to cosmic distances. Experiments have verified light speed's constancy to parts in 10 to the 17th power, confirming it remains unchanged regardless of light's frequency, the source's motion, the observer's motion, gravitational fields, or cosmic epoch within experimental precision. This extraordinary constancy suggests light speed represents something fundamental about spacetime's structure rather than merely a property of electromagnetic waves, possibly indicating a maximum rate of causality built into the universe's fabric. The lack of variation, despite exhaustive testing, strengthens confidence in relativity's foundations, indicating that the universe respects this cosmic speed limit universally and exactly, with any deviations from perfect constancy so small that current technology cannot detect them, suggesting C truly is an invariant feature of nature. The fine structure constant relates light speed to other fundamental constants, appearing in formulas connecting the charge of an electron, Planck's constant, and light speed through the dimensionless number approximately equal to 1/137, whose value determines the strength of electromagnetic interactions. This constant describes how strongly electrons and photons interact, governing atomic structure, chemical bonding, and electromagnetic phenomena throughout the universe. Yet its specific value remains unexplained by current theory. The fine structure constant's dimensionless nature makes it universal. Unlike quantities measured in meters or seconds that depend on human unit choices, this pure number would have the same value for any intelligent observers anywhere in the universe. Why this constant takes its particular value remains one of physics' deepest mysteries, with some theories suggesting it might vary cosmologically or could be constrained by anthropic reasoning, but observations show it remains remarkably constant across cosmic history, maintaining the same value that enables chemistry and life. Light speed appears in equations governing electromagnetism, woven throughout Maxwell's equations that describe how electric and magnetic fields propagate and interact, with C emerging naturally from the relationship between these two aspects of the electromagnetic field. Maxwell's synthesis of electricity and magnetism in the 1860s revealed that oscillating electric fields create magnetic fields and vice versa, and these mutual inductions propagate through space at a speed determined by fundamental electromagnetic constants, a speed Maxwell calculated and recognized as matching measured light speed. This remarkable coincidence led Maxwell to propose that light consists of electromagnetic waves, unifying optics with electromagnetism in one of physics' great theoretical triumphs, revealing that visible light, radio waves, X-rays, and all electromagnetic radiation share a common nature, differing only in frequency while traveling at the same fundamental speed. The appearance of light speed in electromagnetic equations suggests C represents something basic about how space responds to electromagnetic disturbances, not merely a property of light itself. Maxwell's equations predicted the speed of light before it was precisely measured, providing a theoretical calculation that matched experimental observations so closely that Maxwell recognized light must be an electromagnetic phenomenon. By analyzing how changes in electric fields create magnetic fields and vice versa, Maxwell derived wave equations showing that electromagnetic disturbances propagate at a speed determined by electric permittivity and magnetic permeability of space, calculating this velocity at approximately 310,000 kilometers per second. This theoretical prediction came remarkably close to experimental measurements available in the 1860s, differing by only a few percent from more accurate modern values, close enough that Maxwell confidently identified light with electromagnetic waves despite having no direct evidence beyond this numerical coincidence. This prediction represents one of theoretical physics' great successes, demonstrating how mathematical reasoning can reveal nature's hidden connections, unifying apparently separate phenomena under a single theoretical framework through the emergence of a fundamental constant linking electricity, magnetism, and light. The constancy of light speed has been verified in countless experiments across a century, tested in every conceivable circumstance from Earth-based laboratories to cosmic observations, examined from every angle by physicists seeking any deviation from perfect invariance, consistently confirming Einstein's prediction within experimental limits. Scientists have measured light speed from moving sources, measured it in different directions, measured it at different times of year, measured it from astronomical sources moving at various velocities, measured it in strong gravitational fields, searched for variations with frequency or polarization, looked for changes across cosmic history, and found constancy in every case. This relentless consistency across diverse tests strengthens confidence that light speed represents a true fundamental constant, not merely an approximate or emergent property that might vary under extreme conditions. suggesting CE is woven into spacetime's basic structure as an invariant feature that cannot change without altering the nature of reality itself, making light speed perhaps the universe's most fundamental property, the cosmic constant that connects space to time, energy to mass, and causality to geometry throughout existence. And so we complete our journey through 100 facts about light's cosmic velocity, this fundamental constant that connects every aspect of existence from the smallest quantum fluctuations to the largest cosmic structures spanning billions of years. Light speed defines our universe's boundaries and possibilities, limiting how fast information can travel while connecting distant realms through its eternal passage. As you drift towards sleep, let these truths about CE accompany you gently, reminding you that light from distant stars has traveled years or centuries or eons to reach your eyes, that every observation across distance is simultaneously an observation across time, that the universe reveals itself through light's patient journey across cosmic expanses. Rest well, knowing that light continues its eternal voyage through the cosmos, carrying information across space and time at the universe's maximum speed, connecting all things through its constant, unchanging, fundamental velocity.